Okay, let's get started, everyone. So today's topic is the last bit of material that you could be potentially asked about on the midterm next Wednesday. It is on scaling laws for large language models. Before we get into that topic, your homework 2s are finally over. Most of you did very well. Hopefully it was an informative exercise and you learned more about how transformers are actually implemented rather than just like the equations and all the stuff we've been doing in class. Okay, let me briefly discuss the midterm. Obviously on Friday we will spend most of our time reviewing for the midterm, so I'm not going to go take too much time today. But quite a few of you have been reviewing the practice midterms and noted that the problems are pretty difficult and had a question like, are we really expected to solve these questions in 75 minutes in an in-class exam? So no, the exam will not look like the same difficulty as the prior like 2 or 3 years. There are a couple of exams in the resources section from pre-COVID that are more representative of what this exam will look like in terms of difficulty. Obviously back then we had a different set of topics covered in the class, so it won't really help you to prepare for things like naive Bayes that we haven't talked about in this class. But broadly, the format will be, you'll have a couple multiple choice questions. These are generally quite straightforward. There will be, then the rest of the exam is just free response questions like the ones that you've seen in the practice midterms. A couple of them will be on the same level of difficulty as the ones in even the take-home, the take-home exams, but the rest will be simpler in nature. So again, the topics covered you could be asked anything from the first class of the semester to this class here. So best ways to review are making sure that even if you couldn't solve some of those midterm questions yourself without looking up reference material, at least you should understand the concepts and why those answers are, the way they are in the solutions. Again, I've already said this, but you should expect some questions at least on the transformer architecture, the self-attention mechanism. If you look at the practice midterms, almost all of the recent ones have a question about masking in the attention mechanism, but you should be expected to, you are expected to understand, like how it works, what would happen if you change some component of it, and so on. There will be this time a question about implementation. So we might give you like a PyTorch snippet of code and ask you to either debug it or tell us what you might add to complete the implementation of some function. So this is new for this semester because the homework 2 was also new, and so we expect you to be familiar with the implementation side of things as well. Okay, any questions about the midterm? If you were able to do homework 2 by yourself and you understand all of the code that you wrote, then you should be fine for that. We won't be asking you to do things that involve like PyTorch functions beyond what you were asked to use in homework 2. Okay, so with that out of the way, let us get to our topic for today, which is talking about scaling language models. So far, we kind of have not discussed the advantages of scale or why companies like Google and OpenAI are investing so much money to make bigger and bigger language models. So hopefully after this lecture, it becomes clear. So, you know, yeah. Oh, sorry. All right. Luckily, there was nothing useful on the first slide. While this connects, I see a YouTube question. Will we ask you to write code by hand to finish off the function? No. So if we ask you to fill in some code, it will be in the multiple choice section. If we ask you to tell us what's wrong with code, that will be in the free response part of the exam. Good question. All right, so let's get to this notion of scaling. So, you know, for many of you, scaling might seem like it's associated with the number of parameters in the model, right? So if we have more parameters, right, more transformer blocks, bigger hidden representations, bigger embeddings, our models are likely to be more powerful as a result. But this is only partly true, right? There's many other aspects of this whole transformer language model pipeline that we can scale. We can train a model on more data, right? More unique tokens from a data set. We could also train our model using more compute. So let's say we have a fixed data size and a fixed model size. We can train the model for more iterations or epochs, right? So maybe that buys us a better model as well. All of these things are contributing to scaling up the resulting model. And so in the past couple years, we've seen that as we scale in all of these dimensions, model size, compute, data size, we observe these interesting properties that start to emerge, right? So in context learning, when we had that class on prompt engineering, right, we talked about few-shot learning, a model being able to perform a task from a small number of demonstrations, even if the task doesn't appear in its pre-training data set. We saw things like chain of thought prompting that also can arise in pre-trained models just as a function of scale. And also like the ability for these models to be fine-tuned for instruction following. So if you take an instruction following data set, you know, we talked about instruction tuning. If you perform instruction tuning to a small model, it does not generalize to new instructions that are held out. Only larger models seem to exhibit this behavior. There's also more abstract things, right? Like, so if we have a larger model that's trained on more data, perhaps it can memorize more facts about the world and then use them in its responses to held out queries, right? Or maybe it's able to better memorize patterns in the data set that it's seen just due to the added capacity of the having more parameters. And so there's been this like big discussion on emergent properties, which some of you might have actually attended the back-to-back extra credit talks. That one was like, emergent properties don't exist. The other one was like, emergent properties are awesome. Here's why they happen, right? So there's definitely views on whether or not these properties are actually a function of scale and emerge sharply. This was a definition from the paper by Jason Wei, who gave the talk here, called like emergent properties of large language models. The ability to perform a task via few-shot prompting is emergent when a model has random performance until a certain scale, after which performance increases to well above random. So you can see that few-shot prompting is one of the methods by which people are measuring emergence. Like if you have a new task and you just give a couple demonstrations in the prompt, at what scale does the model learn to follow the task rather than just outputting random garbage? And this is a figure from the paper that kind of motivates the advantages of scale. So here we see 3 different tasks, so math word problems. And here they're measuring a model prompted with just the word problem and additionally with chain of thought examples. So the model is forced to like reason about why it's solving the problem in the way it is. So it's interesting to look at this chain of thought curve here. And on the x-axis, we see the number of flops used to train the model, right? So more flops is a function of bigger model and bigger data set size, and also number of iterations. So we see that as you increase the compute budget used to train the model, its accuracy using chain of thought prompting on these math word problems is pretty low until a certain point. And then we observe like its accuracy jumping steadily from close to 0 to about 20% on this task, which suggests that, you know, at some point the model is able to make use of this kind of chain of thought reasoning to better solve these problems. Figure B here is also very interesting, so it's relevant to instruction tuning. Here you have some instruction tuning data set, like the flan data set that we talked about before, and we fine-tune our model on this instruction following data set, and then look at its performance on 10 different tasks averaged together. Again, an instruction following task setup. So we see here that instruction tuning does have a small benefit with these smaller compute budgets, but just like with the math word problems, there's a huge increase in performance from like 40 something to 60 or 70 as we scale up the model to a bigger budget. And finally, probably the most striking thing is on 8-digit addition. Scratchpad is a method that's kind of similar to chain of thought prompting, and you see that as soon as you get to some number of flops, the performance goes from basically 0 to 100, indicating that this ability to do addition via chain of thought prompting does not exist in smaller models, but we see it in scaled up models. Hello, Professor, where can I find homework 2? I hope you're not in the class, but if you are not, you can find it on the website for the course. And if you are, you should do well on all the other things. All right. So clearly, like, scaling is useful empirically, right? We see all these benefits from scaling up the model size and data set size. I just wanted to, okay, you're not in the class. Yes, you can look in the course website. I also wanted to just describe briefly this paper that came out at NeurIPS last year and that won an Outstanding Paper Award, which is a nice counterpoint to the paper from here, Emergent Abilities of Large Language Models. This paper is titled, Are Emergent Abilities of Large Language Models a Mirage? And so the top row here, let's just look at this 2-integer, 2-digit multiplication, 2-integer, 4-digit addition. These are the curves that you see if you measure the performance in terms of accuracy. So accuracy is just a binary judgment. Is the answer correct or is it incorrect? And the argument made in this paper is that although if you're using these like sharp, discrete metrics like accuracy, the curves look very sharp as a result. Like your accuracy here is 0 until you hit 10 to the 10th parameters, and then it starts increasing. So this is the emergence claim that is being made in the prior paper. But if you use a different metric that is more continuous, so here they're using the token edit distance. So in these math problems, what that basically means is you have like some ground truth answer, and you have your model's prediction, and you measure how many digits that of your model's prediction are correct. So maybe it got like the last digit right, but failed on one of the other digits. In accuracy, this would get a score of 0, but with token edit distance, it still gets some partial credit, even though the answer is wrong. So if you're measuring with a smoother metric, then the curves start to look pretty smooth as a result. So with increasing the model size, we do seem to be improving on the smoother metric, even though improvements on accuracy are only seen at like 10 to the 10th parameters. So maybe emergent properties really don't exist and they're just a function of like how we're measuring the model's performance. But regardless, it's clear whether or not you believe in emergence that scaling is definitely helping, regardless of what the metric is, right? In both cases, these curves are going up, right? The performance is increasing with scale. So it's not arguable that scale is helpful, right? It's clearly helpful. All right, any questions about this so far? Okay. So now let's turn to what can we scale, right? The model size is the most obvious thing, but also, as I mentioned, the data set size and the amount of total compute. Most people are mainly concerned with the latter, right? Because it's the most practical thing. Let's say I'm, a UMass PhD student. I have access to, at most, let's say, 4 to 8 GPUs to train my models, right? And I also have a fixed amount of time that I can train my models for, right? I can only use those GPUs for, let's say, a week max. So if I wanted to train a language model on 4 GPUs for a week, right, that is my constraint. I know that I want to use all of that time, the compute time, to train my model. Should I pick a small model and train it on a larger data set? Should I pick a huge model with a smaller number of tokens trained? How should I allocate my compute? That is the key question behind these scaling laws. They always assume you have a fixed compute budget and you're trying to figure out what you should do with your model size and your data set size. How should you balance those? And basically the question is, if someone gifted me, one more week of compute, how should I allocate the resources, right? That's the question that these companies are most interested in. Okay. Again, this is just reiterating what we discussed before. Given a fixed compute budget, what is the optimal model size and training data set size for training a transformer language model? And this is not an easy question to answer, right? Because if we wanted to empirically measure this, we would have to train a huge number of language models with different compute budgets, varying the model size and data set size, and then try and fit some sort of curve to predict for unseen compute budgets what the optimal ratio would be. Luckily, both OpenAI and Google have done these experiments and released their results so that anyone can, given a fixed compute budget, figure out what the optimal model and data set size for that budget would be, given their constraints. Okay, so let's make it more concrete here. We might want to be asking these questions, like if you were able to use 1 GPU for 1 day, would you train a 5 million parameter language model on 100 books, or 500 million parameter language model on 1 book, or a tiny 100,000 parameter language model on 5,000 books, right? Which one is best? So we'll start with OpenAI's paper that was released in 2020, this Kaplan et al. Paper. It's called Scaling Laws for Large Language Models. And some of the highlights, the takeaways from this paper are still relevant today. So the first takeaway is that the performance of the language model depends strongly on the scale, like the total number of model parameters, data set size, and compute. It does not depend so much on the shape of the model. So like how many layers versus the width of each layer, things like how many heads are allocated in each transformer block. These are all hyperparameters that might matter more at smaller regimes, but as you increase the scale, the size of the model, it seems like just the raw parameter count is all that matters, especially when you get into the billions tens of billions of parameters. So this is kind of useful when you're thinking about hyperparameter tuning, right? There's a lot of different, hyperparameters in terms of what's your word embedding dimensionality, what's your model dimensionality, your internal like query key value dimensionalities, how many heads, etc. These things may not matter so much when you're getting up to some huge scale. Next is that the performance of the model as a function of scale can be modeled with power laws. So all of these papers that we will see today are trying to fit power laws between the test loss of the model. So imagine like the perplexity of the model as a function of model size, data set size, and compute budget. So we want to find some power law relationship that allows us to extrapolate to compute budgets that we haven't observed any data points for yet. And in general, like your performance, your test loss, your perplexity, it improves most if you concurrently scale up the data set size and the model size together as you get more compute budget. So you might think, I could just allocate all of my compute to model size and train on a very small data set. But it turns out that data is just as valuable as the model size. So the Chinchilla scaling law basically tells you that you should scale both the model size and the data set size proportionally to each other, like 50-50. You find the best performing model in the middle, so not overvaluing either model size or data set size. And the final takeaway that is still relevant today is that, there's a lot more in this paper. If you're interested, you should check it out. But the one takeaway that I want to highlight is that larger models are more sample efficient than smaller models. So to reach the same test loss, they require fewer updates than bigger models. So this is another advantage of scale, is the sample efficiency of these models. So we'll see that in this plot here. So if you look at the plot on the left, and the plots that I'm going to show you today are quite complicated, so I'll spend some time explaining them. There's a lot of different variables here. So first, we see all these curves of different colors. Each curve corresponds to a different model's training run. So you can see that the x-axis is number of tokens processed by that model. So how many tokens has the model been trained on and backpropped on? The color is a function of the number of parameters of the model. So these yellower colors are associated with bigger models, like billion scale parameter models. The smaller models are very small, like thousands of parameters. So let's start with the small models here, which are these bluer curves. We observe that as the small model sees more tokens, the test loss decreases to some point, and then it kind of flattens out, indicating that you can keep feeding the model with more and more data, but it's not improving anymore at generalizing on the test set. Like the perplexity is flat after some point. So the model is not benefiting from this additional data. That's basically what this is showing. Now let's look at the billion scale, the yellow curves here, which are the biggest models in the plot. We see that as you increase the data set size, the curve keeps going down, and even at this point, when it's seen like hundreds of billions of words, the curve is still not plateaued, right? So this indicates that only larger models can benefit from more training tokens. And then we can also look at, let's take a specific loss threshold, let's say 8 here. How long does it take? Like how many data points does it take for a small model to reach this target threshold versus a large model? So if we look here, it looks like our tiny model reaches this threshold around 10 to the 9th tokens if our target threshold is 8. Whereas our our bigger model, this yellow curve here, reaches a loss of 8 at maybe 10 to the 8th training tokens, right? Indicating that it is more sample efficient. It's reaching the same loss with fewer updates to the model. Okay, does that make sense? So one takeaway from this plot is that with smaller models, after some point, just increasing the data size, or in this right plot, you see the compute plotted here, so just the number of floating point operations used to train the model. You see that for the smaller model, regardless of how much compute you throw at it, there is some regime where it starts to plateau and does not improve any further. So if you want your model to achieve lower loss, then scaling the size of the model is a good way to achieve that. Basically the takeaway here. Any questions? Okay, so I'm not going into too much detail on this particular paper because later on it was found that there were some issues with the experiments that they ran. The major issue was that they used the same learning rate schedule for all of the training runs that they did. So like this, all of these curves in this plot, regardless of what the data set size was or the batch size, how many batches they were training for. So the learning rate schedule is essentially a hyperparameter of the training process where you specify at different points during the training. So let's say 10% of the tokens have been seen, 20%, 30% in an epoch. How should you change the learning rate? So it's very common to start with a low learning rate, and then as training progresses, sharply increase the learning rate, and then after some point start to decay the learning rate again. This kind of schedule is very common in training large language models, and the point at which you start to decay the learning rate is a function of the data set size and the number of iterations that you've been training. And they use the same schedule regardless of what the number of training tokens and batch size was, which obviously impacts the results because this is actually an extremely important hyperparameter for transformer models. So this kind of impacted the resulting power laws that they were able to fit. And as such, people who were following these scaling laws trained some suboptimal models in the process, as the next paper we're going to discuss shows in depth. All right. So that paper was done by Google and is called Chinchilla. And so I'll just give a high-level picture of the differences between OpenAI's paper and Google's. And then we'll go into more detail about these Chinchilla scaling laws. So this Kaplan et al. Paper from OpenAI, the takeaway was that you should prioritize increasing the model size over the data size if you have a fixed compute budget. So with a 10x increase in compute, so let's say I was able to use my GPU for 10 weeks instead of 1 week. They said you should increase your model size by 5 times and your data set size by 2 times if you have this kind of 10x compute increase. And with a 100x compute increase, your model size should increase by 25 times and your data set size by only 4 times. So for a couple of years, this is what a lot of other companies did. They scaled their models using this scaling law. This Chinchilla paper says, well, we fixed your issue with the learning rate and we found a completely different scaling law, which actually suggests that you should increase both the model and data set size at the same rate. So with a 10x compute increase, instead of increasing the model size by 5x, you should only increase it by 3.1x, and your data set size should also be increased by 3.1x. And both model and data set size 10x when the compute is 100 times more than you originally had. So you can see that, just this one decision of fixing the learning rate schedule had a dramatic impact on the resulting power law, right? And the conclusions that we can draw to extrapolate to new compute budgets. And all the models trained before this Chinchilla paper came out, as a result, were really big, but they didn't prioritize the data size, and so they were as a result suboptimal. Okay, yes. You should scale both. Yes, that is, like kind of what some of these plots are. Whoa. Okay. Yeah. So that is one of the conclusions in their paper, and several of their plots show that, like, if you only increase one and not the other, you run into diminishing returns and plateaus. What do you mean the same rate? Well, they specifically tell you you should increase the model by this rate and the data by this rate. So just to step back and maybe clarify a little bit further, the issue with, so how do we get these kinds of statements, like you should increase the model size by 5x and the data by 2x? They trained a ton of language models with different data and model sizes with the same budget, and then looked at, like, for each fixed compute budget, when did I get the best performing model, like in terms of perplexity? And they tried this for a bunch of different compute budgets, and then fit power law to predict, like, for some test compute budget, what is the best balance of these two. So that's, both of these papers did the same, like, fitting a power law, but obviously their conclusions are very different based on the data. All right, other questions? Yes. Yes. So the question is, based on the Chinchilla scaling laws, we would be training a smaller model on more data. That is correct. That's like the optimal to minimize your test loss. So wouldn't there be overfitting? Overfitting is, it's a little unclear what that means in the context of language models. We will talk a little bit about the effect of repeated data. So, like, let's say you have 100,000 tokens in your training data set, and you're not going to get any new tokens. So one way to increase the data set size is just to train your model for more epochs, right? So it sees the same 100,000 tokens at every epoch. I think it's still not, like, well known what the impact of the repeated data is. Some people think that it's beneficial, others say it actually hurts quite a lot. But yeah, I don't think any of these models is overfitting, because the training corpus is so huge that if you look at the training loss, like, it's not going to zero on even these huge scale training runs. Yeah. All right. So this is the most important plot in the Chinchilla paper, and just like in the OpenAI paper, it is quite complicated. So let us break it down. So here we see a bunch of different curves. Each curve is a fixed compute budget. So these numbers are all basically a function of the flops used to train the model. So if we look at this lightest curve up here, all of the points on this curve use the same number of flops when they were trained. Each dot is a different model. They're all using the same amount of compute, but they vary in terms of the model size versus the number of training tokens. So the points over to the left here are associated with smaller models trained on more data. The points over to the right are bigger models trained on fewer data points. Does that make sense? So you can see the x-axis here is the model size from 100 million to 30 billion. And one conclusion from this plot is that, well, the bigger model is not always better for a fixed compute budget, right? So the biggest model trained is always the one to the right of each curve. You can see that actually in no case is the bigger model the best model. In fact, the optimum model is always somewhere in the middle, right? So it's like for each compute budget, you pick a model size somewhere in the middle and a data set size somewhere in the middle, and that's where you get the lowest test loss. One caveat is that here they report training loss on the y-axis, but they're using the training loss as an approximation for the test loss, and they have some good reasons in their paper why they can do this. But basically, we care about the test loss, right? The perplexity on a test set. So that's what they're trying to measure. Okay, so just to be more clear, right? We want the ability for any arbitrary compute budget to figure out how big should my model be and how much data should I train on. Here, I only have, I don't know, like 10 of these curves, right? So if I have a new compute budget that's much larger than any of these, I want some ability to extrapolate from this data here. So what they do essentially is they take the minimum of each of these curves and they plot the minimum as a function of the data set size and the model size. And that's how we get these two plots here. So each dot here corresponds to the minimum on one of those 10 curves from the previous plot. And then they fit this curve through all of these minimums, which allows them to extrapolate to some much larger compute budget. And so it's very easy to fit a curve and say, all right, I have a scaling law and this is what you should follow. But obviously, in order for people to believe this, they need to show it at some much larger compute budget. So they pick this compute budget here, this number of flops, like 10 to the 24th, as where they're going to experiment with. So all of their experiments on this plot were done at much smaller compute budgets. So now they want to see if this curve here extrapolates to a much larger budget. And so based on this extrapolation, they find that for this very large compute budget, the optimal model size is 63 billion parameters. And for the same compute budget, the optimal data set size is 1.4 trillion tokens. So now, in order to prove that this is actually, this scaling law is better than the Kaplan et al. Scaling law, what they do is they train two models. One following this model size and data set size as specified by their scaling law, and another with the same number of flops that follows the Kaplan et al. Scaling law. And so here we see the two models that are compared. I believe this Gopher model is using the same Kaplan et al. Scaling law. So it's a much bigger model, 280 billion parameters, but it's trained on only 300 billion tokens. And their Chinchilla model, using this new scaling law, is 4 times smaller. It's 70 billion parameters, but trained on much more data, 1.4 billion tokens. And so now, how are we going to measure which model is better? We can simply just evaluate the test loss, right, the perplexity, and see which one is actually better. All right, so I want to just go in a little bit more into the details. I was going to do this on the iPad, but I will just show my notes because my pen stopped working. But one thing to highlight before that is that this compute budget here, so the total number of flops, what is that a function of? They use this approximation here, 6 times n, which is the number of parameters in the model, times b, which is the batch size, times s, which is essentially the number of iterations, the number of batches that the model sees. So basically your compute increases for one batch if your model is a lot bigger, right? A smaller model is going to take much less flops than a larger model to do forward and back prop over one batch. And then the rest of it is just how many batches do you have and how big are those batches. Okay, oh, there's a question here. With many models now being multimodal, how do we view size of data across modalities? Do we calculate them separately, or are there some conversion normalization method? That's a really good question. I'm sure there are papers on multimodal scaling laws. I don't know what the conclusions are or how they address this problem. There are many ways of tokenizing images, so I would actually be curious about the answer to your question as well. But no, I don't actually know. Okay, so let me go to my notes here. So I just wanted to formalize all of these things in more detail so that you're able to understand the paper better. So the thing that we care about is this test loss, right? Like, how well is our model able to predict the next word on data that it's not trained on? So they call this L, just the average cross-entropy loss of your test set. We'll have a few more variables here. D is the number of training tokens for this pre-training of your model. N is the number of parameters in your model. So again, like a transformer model, right? It has parameters in the embeddings. It has the self-attention, like query, key, value, weight matrices, the feed-forward layers, and so on, right? So adding up all of these parameters together to get one number. And finally, C is the compute budget. So the number of flops that is used to train this model, which, as we just discussed, is a function of the model size, the number of parameters n, and the data set size, number of tokens d. Hopefully that notation is clear. So now, given a fixed budget of flops, C, we are trying to solve this optimization problem. So this is the key thing in this Chinchilla paper. So we want to minimize this, so we want to find the values n and d, right? The number of parameters and number of tokens that minimizes the loss. But we have these constraints that the number of flops used to train this model is equal to some fixed value c. So if you know ahead of time, I only have this compute budget to train this model, you're trying to solve for n and d such that you minimize the loss. Does that make sense? This is the goal of all of these kinds of scaling law type things. And so the Chinchilla paper breaks this into this power law, where the loss of a model with n parameters trained on d tokens can be modeled with this equation here. And so there are many different parts to this, which is what I wanted to discuss. So we are essentially trying to find values of A, which is A and B, which are constants, alpha and beta, which are these exponents over n and d, defining the power law, and E, which is this other constant that we're estimating. So let's take a look at what each of these things means. And we can start with E. So we see that E is not associated with the model size or the data set size. So you can view this as we're trying to estimate the loss, right? So if we have like an infinitely large language model trained on all the data in the world, essentially like a perfect language model, we couldn't do any better in terms of model size or data set size. Our loss would not be zero, right? Our test loss just cannot be zero because we know how language works, right? At any point, if I have a prefix and I want to predict the next word, there's going to be many plausible choices for most prefixes, even given all the context you could possibly give the model. So even like the best language model will have some non-zero loss, right? And so that's what we are trying to estimate with E, is this like minimum loss that a perfect language model would have on some held out data. The other terms are quite straightforward, right? So this term here is essentially like, okay, so I will never have this perfect language model, and I'm always going to be bounded to some extent by the number of training tokens that I have, right? So this data size, the limitation that I have in terms of only having a fixed number of training tokens, is also going to increase my loss by some amount, right? So I'm not a perfect language model. I have limitations on the data set size, so I want to know how much will my loss increase if I reduce the size of my training data set. That's what the second term here in the middle is referring to. Like, what is the contribution of the data set size to the optimal loss, the minimum loss? And the first term is the same thing except for the model size. So again, like this E term here is basically imagining we have just an infinitely large model that's not bottlenecked at all by the parameter count. But in practice, we're always bottlenecked by parameter count, right? Based on how much memory we have on our GPUs, et cetera. And so with smaller models, we're going to have a higher minimum loss. We already saw that in the plots that I showed you from the Kaplan et al. Paper, right? And so that contribution of the loss based on the model size is going to increase as you have a smaller model with fewer parameters. Okay, so we have this equation here. Any questions about this? So alpha and beta are things that we're trying to learn, these exponents that we're trying to fit based on empirical training runs of, so I have, let's say, a fixed compute budget. I've trained many different configurations with varying N and D. And so you can think of it as trying to fit like a curve to the empirical losses that you observe through these training runs. A and B as well. So we'll see this shortly. So okay, here we go. So maybe this will be more clear for you as well. The Chinchilla paper, the main takeaway is that they train a bunch of different models with different compute budgets, and they fit this model that was just described by the prior equation, and they find the following coefficients here. So this E variable is 1.69. So basically, in our interpretation, the loss achievable by this perfect language model, not bottlenecked by model size or data set size. The alpha, which is the model contribution, model size contribution, is 0.34. The beta is 0.28, and A and B are set to 400. So this is the equation with these values that they use to extrapolate to the, the Chinchilla model that they got with whatever 70 billion parameters and 1.4 trillion tokens. That is what this equation tells them will achieve the minimum loss with their flops budget. Okay, so let's take a look at their results, which is also now we can interpret in terms of these variables. So they had the same compute C, the same number of total flops for both Gopher and Chinchilla. We already went over the size of the model and data set. So the loss achieved by Gopher is 1.993. The loss achieved by Chinchilla is 1.936. So this may seem like a very small difference to you, but it's actually substantial in language model training. So even these like tiny differences in the loss can be very meaningful on downstream tasks and for like emergent behavior and so on. So and their experiments show that like this model here, Chinchilla, is actually much better than Gopher across many downstream tasks as well, not just the perplexity is better. And they also say in their paper that based on their scaling laws, with this compute budget, no model trained with 300 billion tokens could ever be better than this Chinchilla model. So you would need to increase your compute budget by a lot before you would get a 300 billion parameter model that would outperform this small 70 billion parameter model. So yeah, hopefully you understand, what these scaling laws are, how they're fit, and what the implications are. There could also be errors in this Chinchilla scaling law, by the way. Like, these are all fit on empirical language model training runs, right? And the hyperparameter configuration and everything needs to be very carefully controlled to enable extrapolation. You have a question? Mm-hmm. Yeah.
So here we are just using perplexity. So which scaling of change if we use other methods?
Yeah, that's a great question. So all of these scaling laws only depend on the loss, right? The perplexity. They're not functions of like task-specific performance, like translation or factuality or anything else like that. Would the curves change if we instead were more interested in like how often does a model hallucinate given this budget of model size and data set size? I bet it would. There's no real way to tell. Measuring those things is difficult, right? It's unreliable. It's much slower to evaluate than the loss, which you just get as a function of like the forward prop step. You get the probability, so you can already compute the perplexity. But I think it's a good question. Unfortunately, there's only like 2 companies that can redo these experiments. So yeah, I can only speculate, but it's definitely a good insight. Mm-hmm. Yeah, that's also a good question. So, like, how practically useful are these scaling laws? If you actually look at Llama 2 and Mistral, they don't follow the Chinchilla scaling law. They're actually overtrained for the size, like a 7 billion parameter language model. You would get from these scaling laws that you should train this for like some, I don't know how many billion tokens, but they're actually trained on far more tokens than the Chinchilla scaling law would say. Like it would tell them to scale up the model more if they wanted to train on that many tokens. So I think in practice it's kind of mixed. One very important thing that is not covered in this Chinchilla or the Kaplan et al. Scaling law paper is the inference cost as well. So if let's say you're a language model provider and you know that billions of people are going to be using your language model, in that scenario, it is very important for you to have a small language model, right? Because you don't want to be using so much of your compute at test time on any individual query. So it might be optimal for you to actually overtrain a small language model, even though you see diminishing returns, just because a bigger language model is not practically usable. So there was actually a follow-up paper to Chinchilla that accounted for inference cost as well, and showed that the curves really change a huge amount when you consider like how many users of your model do you expect to have. That paper was done by Mosaic ML, which is now in Databricks. So it's a very useful paper. But yeah, as to your question, practical considerations always seem to dominate. So these are just like rough guidelines. We'll see. They'll probably be updated next year. All right, any other questions? Yes. Yeah, that's a great question. So the question is, do these scaling laws apply if you're doing some non-standard things like taking a big model and pruning it? Another related question is, what if you're doing distillation, right? So you have a big teacher model and you want to distill that into a smaller model. Like, how do these scaling laws affect this kind of scenario? These only apply to the case where you're training a model from scratch on a huge amount of data. I have no idea if they are meaningful at all for cases where you're starting with some existing model and trying to distill or prune it. I would suspect they don't hold up, but there might be other scaling laws in that scenario. Like in the distillation setting, it's quite interesting because in distillation generally have a teacher model that has already been trained, let's say like GPT-4, and you have a student model that you're interested in training. And so you have this other question, right? Like, how many examples from the teacher should I get versus how big should my student model be? And there could be similar scaling laws, but yeah, I would expect they would be very different. It's a good question. Okay, let's move on. So this is another figure from the Chinchilla paper that just kind of highlights how misguided previous attempts were for LLM training. So this dashed line here is like the model size that you would get for a fixed compute budget if you followed the OpenAI Kaplan et al. Scaling law. And you see GPT-3 was trained according to this scaling law. The Gopher model that we just mentioned was also trained using this law. And Megatron Turing NLG, I forget if I think this is by Microsoft. It's actually a huge model, 530 billion parameters. But again, it is under-trained. It was not trained on enough data because it was using this other scaling law. Meanwhile, you see Chinchilla, which is over here on this other curve, with the same compute budget as Gopher, but is only a 70 billion parameter language model. Since Chinchilla came out, I think we've seen more efforts to be on this end, and even more favoring the data scaling rather than model scaling. Okay, so let's end with the type of data. So if I can increase the data set size, what is the best way to do that? Do I need to get new tokens? Like if I want to go from 10 billion tokens to 100 billion tokens, can I just repeat my data set 10 times? Or do I need 90 billion new tokens? Most of the training data for these LLMs comes from the internet, right? The Common Crawl is the main source of training data for all LLMs, which is just a giant scrape of the internet. And so obviously there are better sources of data. Like imagine you could get all copyrighted published books that were ever written. And many companies are training on copyrighted text, right? OpenAI's models Mistrals. Any company that doesn't release their training data is likely not releasing their training data because it contains things that they may not want people to know that are in there, right? There were actually many suspicions that some of these huge LLMs were trained using a dump of a pirated like book website that you know, like many of you have probably used to download textbooks for free or whatever. You know, if you're a company, why not just download all of those books and use them in your training data? Because that's obviously much higher quality than the internet. So I suspect we'll be seeing a lot of legal battles forthcoming once people actually figure out reliable ways to say, like, was GPT-4 trained on this book, or yes or no? And if you're the author of that book and the answer is yes, you might want some, you know, money, right? Okay, so that's one thing. And if you see like two different models and one is trained on an open data set and the other is trained on an undisclosed data set, the latter is almost always going to be better. So like Olmo, for example, that model we were playing around with a couple lectures ago, is trained on a fully open source data set that largely comes from the internet, like the Common Crawl. This model is much worse than Mistral, which does not disclose their pre-training data set, even though it's the same size, and probably has been trained on a similar number of tokens. So it's not just the size of the training data set, but also the quality of the data set that matters. But quality is like much more nebulous to you know, quantify into some number that can be fed to like one of these scaling laws, right? So right now it's just kind of empirical results suggesting that data quality is extremely important, but how important it is, we don't really know. So, okay, let's just talk about this. What is the impact of repeated data first? There's two competing views. One from OpenAI suggests that repeated data can lead to severe degradation in performance. So they have this nice quote: performance of an 800 million parameter model can be degraded to that of a 400 million parameter model by repeating just 0.1% of the data 100 times, despite the other 90% of the training tokens remaining unique. So it suggests that data repetition is actually very harmful to the model's ability to predict the next word. However, it's unclear if this phenomenon actually exists with much larger models, like 800 million, 400 million are still on the small end, and perhaps larger models are less sensitive to like multiple epochs or repetitions of the training data. Meta's Galactica model, in their paper, they actually found the opposite result. With a much larger model, they said they trained their model for 450 billion tokens, which is 4.25 epochs. So they see every training example 4.25 times. We find that performance continues to improve on validation set in domain and out of domain